Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss some applications of operational amplifier. Operational amplifier, the IC that maximum we will be taking are IC741 op amps. Okay, so they are applied for linear and non-linear applications. The different linear applications I have listed here. They will be acting as adders, subtractor, voltage follower, current to voltage converter, voltage to current converter. They will be acting as integrator, differentiators, and active filters. So, active filters are those which employ transistors, these kinds of operational amplifiers, along with some resistors and capacitor, and they will be acting as filters. Another nonlinear applications are comparators, log amplifiers, exponential amplifiers, peak detectors, precision rectifiers, waveform generators, clippers, and clampers. So, few examples and their respective circuits we'll be discussing in this video. The first example I have taken is a summer, how the operational amplifier is applied for summing two or more voltages. So, this is the symbol of an operational amplifier. The inputs are an inverting input. It has two inputs, one inverting and the other one non-inverting. A feedback resistor is connected to the op amp. And here we are going to feed in three inputs. We are going to feed in three inputs to the inverting terminal of the op amp. What does the inverting terminal do is, if you are feeding one input voltage to the inverting terminal, the output will be 180-degree phase shift. For example, if we are feeding in 2 volts, the output will be minus 2 volts. So we are taking 3 input voltages. We are feeding in 3 input voltages. These kinds of voltages with V1, V2, V3 voltages with resistors all equal values, hence I have named them R values of resistors. So these will generate some input current I1, I2 and I3 current will be passing through the respective resistors. The other terminal, that is the non-inverting terminal, is grounded. Let the potential at the input terminal be VA and this terminal be VA at the input. Let the resistor here be connected. It's a feedback resistor and it is named as RF, and I current flows in the circuit. V0 is the output voltage. We will be collecting the output voltage across this terminal. So how to find the value of the total output voltage? So using KCL, the total current I will be equal to I1 plus I2 plus I3. But what is I1? I1 will be the difference of I1 will be the difference of these two potentials, VA and V1, VA and V2, VA and V3. Yes, so I1 will be equal to VA minus V1 divided by R plus what is I2? I2 is a current flowing through R resistor and its value will be equal to VA minus V2 divided by R plus what is I3? VA minus V3 divided by R is equal to 0. So simplifying VB is at ground potential and hence VA is also equal to 0. Why? Because this VA and VB are equal. So therefore, simplifying this, the total output voltage is equal to minus RF divided by R into V1 plus V2 plus V3. And if RF is equal to R, then V out will be equal to minus of V1 plus V2 plus V3, because we are feeding the input voltage to the inverting terminal. The output voltage will be the inverted voltage of the sum of the voltages V1 plus V2 plus V3. Hence, the operational amplifier is acting as a summer. The same case, if all the three voltages are applied to the positive terminal, then V0 will be equal to V1 plus V2 plus V3. Yes. So, in case the voltages are applied, three inputs are applied to the positive terminal or the non-inverting terminal of the op amp, we'll try to obtain the output voltage. Hence, the previous circuit is an inverting summing amplifier. If we are feeding the input voltages to the non-inverting terminal, then the circuit is called non-inverting summing amplifier, non-inverting summer. So V1 will be equal to R by 2 by R plus R by 2 into VA voltage plus R by 2 divided by R plus R by 2 into VB plus R by 2 divided by R plus R by 2 into VC. Then simplifying, we will be getting V1 is equal to VA by 3 plus VB by 3 plus VC by 3 is equal to VA plus VB plus VC divided by 3. And if RF is equal to 2 times of R1, 1 plus RF by R1 is the gain of the non-inverting terminal, which is equal to 3. So this is the analysis for non-inverting summer. We have another mathematical circuit called averaging amplifier. What is averaging amplifier? A summing amplifier can be made to produce the mathematical average of the input voltages. The amplifier has a gain of RF by R, where R is the value of each input resistor connected. The general expression for the output of an averaging amplifier is, we can also calculate the average. So V out is equal to minus RF by R into V1 plus V2 plus etc. up to n value of voltages, n input voltages. Averaging is done by setting the ratio RF by R equal to the reciprocal of the number of inputs, that is RF by R is equal to 1 by n. Yes. The next mathematical amplifier is difference amplifier. Difference amplifier. I'll draw the circuit of a difference amplifier. This circuit will calculate the difference of the two input voltages fed at the inverting terminal and the non-inverting terminal, and it will amplify that difference. We have already discussed a differential amplifier using PCT in the previous video, isn't it? In the same manner, V1, V2, R1, let the feedback resistor be R2. So the input resistors are R1 and R3. They are maintained at the potential of VA and VB. Through another resistor R4. V0 is the output voltage. So when the supply voltages are given V1 and V2, the op-amp will calculate the difference in the signals and it will amplify. If R1 R2 is equal to R and R3 is equal to R4 is equal to RF, then according to KCL, we will be getting VA minus V1 divided by R1 plus VA minus V output divided by R2 is equal to 0 because the same current flows through. Since VA is equal to VB, VA is equal to VB, VA is equal to VB is equal to R4 divided by R3 plus R4 into V2. And V0 is equal to R4 divided by R3 plus R4 into R2 by R1 plus 1 into V2 minus R2 by R1 into V1. So therefore simplifying we will be getting V0 is equal to RF divided by R into V2 minus V1. The value of the output voltage is the gain into the difference between the two input voltages V2 minus V1. This is how we get the output voltage of a difference amplifier. Yes, we'll move on to another mathematical circuit called adder subtractor. The circuit will do both addition operation as well as subtraction operation. We will take 4 resistors, all of equal values. 2 resistors being connected to the inverting terminal and other 2 resistors connected to the non-inverting terminal. The feedback resistor are and the input resistance are of the same values. V1, V2, V3, V4 are the input voltages fed to the adder subtractor circuit. Assuming all the values of resistors are equal, they are fed to the inverting and non-inverting terminal of the op amp in this manner and are held at potentials VA and VB. Is RF is equal to R. Therefore, what will this operation be performed is the sum of the voltages V1 and V2 and V3 and V4 will get added, and these two, when fed to the op amp, the output voltage V0 is equal to V3 plus V4, sum of this minus V1 plus V2, because V1 and V2 are fed into the inverting terminal. Yes. So the amplifier has done the operation of both addition as well as subtraction. This is possible to be performed simultaneously with a single op amp. Yes, the output voltage V0 can be obtained by using superposition theorem to find the output voltage V0 due to V1 alone. We can make all the other input voltages V2, V3 and V4 equal to 0. After making that, then the simplified circuit will be V03 across individual voltages if we want to know. V03 due to V3 alone. What is the effective output voltage due to V3 alone? Then superposition theorem has to be applied into the total voltage VA, which is equal to 3V3 by 3 is equal to V3. Similarly, this can be shown at the output voltage V04 due to V4 alone. Thus, the output voltage V0 due to all four input voltages are given by V0 is equal to minus V1 minus V2 plus V3 plus V4. And the other component is the op amp is also acting as scaling adder. Scaling adder. A different weight can be assigned to each input of a summing amplifier by simply adjusting the values of the input resistors. Then the output voltage for this can be written as V0 is equal to RF by R1 into Vn1 plus RF by R2 into Vn2 plus RF by Rn into Vn. This is the output expression of a scaling adder circuit. In this video, we have discussed some mathematical applications of op amp like adder, subtractor, difference amplifier, and scaling adder. Thank you.